So once again, we are welcome to the presentation for this live session of our regular program. And as I said, today we are going to continue with the application of machine learning in crop production. And then I do hope that we are hearing me clearly and we can see my screen. You can type for me to know you are hearing me, please. And if you have any issue, you can respond to us by just typing or expressing your message so that administrator can take care of it as soon as possible. So we've had, this will be maybe the third series and cumulatively the sixth series, because we had 3 series before. However, okay, thank you very much for the feedback. It's good to know that everybody is hearing us loud and clear. Thank you. So we started some weeks ago where we had 3 sessions on AI and machine learning in crop production, in agriculture generally, and we try to sensitize us on some of the possibilities. Starting from 3 weeks ago, we came back again to it, and then we try to again analyze for that practically. How can we do it? It's not just theoretical. And we've had opportunity to run models, build our model for the first time. And the good thing is everybody's always welcome. And we are aware of the fact that some people are just maybe joining for the first time. I can assure you, you have nothing to fear. Just try to subscribe to the WhatsApp group, and then also subscribe to the YouTube channel. And then whenever videos are posted, sometimes we do post video based on questions from people behind the scene, just to carry our followers along, to carry them along and clarify the challenges they may be facing. And you're always also welcome to contact us offline if we need guidance. So together, the principle of our system is machine learning for all, AI for all. Everybody can actually utilize machine learning in his or her own way to improve or to facilitate its own area of specialization. And then this is what we set to do a long time ago, and we are still on it. And thank God that we are making progress and people are taking benefit. So on the revisiting of practical demonstration in Weka on crop production, we had it. Agriculture is an age-long means of livelihood of millions, if not billions of people. So you can't do without it. So, and the global demand for agricultural products kept increasing as the populations also keep increasing. And not only that, people with financial capability also want to eat many things at a time. So when they set up the table, there are so many varieties, which means more food are being consumed, even though some of them ended up being wasted. So how can we improve production without necessarily also depleting the natural resources, as the case may be? So we look into technological know-how and we can benefit from machine learning. We have done this. Again, we revisit it again, telling us the basic and the ingredient is your data. Once you have data, you are set to go. Get your data. Getting the data could be a problem. We've recommended to us that we should try to start from online data. Go online. Go to some of those websites we've recommended for you, like Kaggle, Kaggle, or UCI repository, and so many other ones we've been posting, and we continue to post it on our WhatsApp group. You can get a real life data or a data that's been posted there. We can then start from a place. Once you have the data, then start thinking of how you are going to gather your own data, because it's so simple. Generally, anything where you can have a relationship, like y is equal to f of x. This is the idea of machine learning in simple terms for the layman. We have y in crop production we have been modeling is yield. That is how much of agricultural product can I produce subject to some variables like amount of fertilizer use, pesticide use, the state where that particular plant is to be planted, because state has their own unique characteristics, the period of the year. So these are called independent variables. So we have a function. We are looking for a function that can be able to understand what is the relationship between all these variables that can influence the amount of yield that we can produce. So if we are able to come up with this kind of function f, which we don't know at the beginning, that is why in machine learning, we basically have the very common one, the supervised learning, which is divided into training, and then testing. Training and then testing, and then testing. So during the training, we are looking for this f. See, during training, we are trying to look for this f that will give us the best possible outcome later on. So that means if you want to build a model, you need to look for data whereby we know y and x, they are known. They are known. This is what we call training set. So we are now looking for f, which is unknown during training. Then after the training, f will be generated, which we call hypothesis function or model. And then we can take that hypothesis function. During the testing stage, then we have y that is unknown. Of course, in the testing stage, we know that y, but we will keep it secret. We don't expose it to our model. We want to check if what we have trained is actually going to work. So we know why, because it's part of the data given to us, but we divide the data into training set and testing set. For the training set, we know y and x, and we give y and x to the machine learning algorithm. Let him figure out what is going to be the function f, the hypothesis function h, that can relate the independent variable with the dependent variable in a very excellent manner. Once we are done with that, although we know the value of y, we will keep it secret. We keep it away from our system. We assume we don't know why. So already f is known. We already found f during training. Now we put the value of x, which is also known. If I plant next year, if I'm going to plant using fertilizer so amount, using this pesticide in this particular part of the country, using so amount of input, what am I expecting as my yield? The system will not predict for us that your yield is going to be maybe 2,000 whatever tons. Since we know why, then we will compare this output that our model has predicted for us. We compare it to the one you are keeping secretly away from it. Then we see how close they are. If you are able to get a system that can estimate with very little error, then that means we can use such machine learning model to actually predict, to estimate what amount of inputs to the agricultural system that we need to add to be able to generate a particular targeted amount of yield. And everybody want to increase yield for sure. So how can we have increased yield without actually compromising the quality of the food and the likes? So this is just, again, to paraphrase what we are trying to deal with. So your data is very important. Without data, you can't do anything. That's why we call it let the data speak series. So once you have your data, then you move to modeling, which is that modeling is what I've discussed now. This is what takes place in modeling. Training, testing, and then you check the performance. Is it okay? Is it better? Is it as I'm expecting? If yes, you are good to go. You can write your report, and then you can benefit from it. However, sometimes it's not that very straightforward. First time, second time, you may not be getting the expected result. Then in that case, you have to go back. You can go back here and do what they call hyperparameter optimization. Hyperparameter optimization. You keep changing the hyperparameter. Sometimes you even change the model. Maybe we started with KNN. Later we move to decision tree. We try different algorithms to see which one is going to work for us. Sometimes we may even go back to the data stage again, like feature engineering. Maybe the features are not good. That's why we are not getting good result. We try to do feature engineering on the data, combine two features to form one, split some features into multiple, like you have date. If you have date as part of the date of planting, we can decide to split it into three. What is the day of the month? What is the month? And what is the year? So you can make one attribute to become multiple attributes. This is called feature engineering. And there are several other things we can do with that. Then we sometimes in the worst case scenario, you may have to go and get data entirely. It means the data you have gotten maybe is not relevant. That's why you are not getting good results. However, if you get good results, why not? You move on. However, you don't need to all these feature engineering at the beginning. Once you get your data and it's working, do the modeling first. That is the principle I call let the data speak. The original data may be perfectly okay for you to get the best result possible. But a lot of people, they envisage the data is not going to be good and they start a lot of pre-processing. I say, no, it's not a good practice. They do a lot of normalization that are not necessary that ended up masking the data, and you will not be able to get the needed insight. The available insight may be missed. So use the raw data as much as possible. And then if it is when the result is not good, then you can keep going backward and refining it until you get what you are looking for. Again, this is a kind of summary of how this system works. Now, because our target is generalization, see, this is the training set upon which you train the model. This is an example. What we are more interested in is what is the generalization power of the model we've built. That's why you have the training set. So we give this to our model. We say this is apple, this is tomatoes. We label it. It's like learning under a teacher. After that, we are looking for F. Once we get our F, we now use that F. This time around, we are not going to tell what is this. We want it to be able to detect what is this. This is an apple. This is tomato. Then we calculate out of 1, 2, 3, 4, 5, 6. How many has been got it correctly? Maybe 5 out of 6. That would be 5 out of 6 times 100. That would be the percentage accuracy of your model. The more accuracy you are, the better. This is called generalization. So our idea is we are not very much keen on the training set. Our target is the testing set. If you are getting better result on training set, because after you train, the same data you use for training, you want to check the performance on the training set. You hide the output, which the system already got exposed to. You want it to predict the training set and see if how much you'll be able to recognize what it has seen before. Sometimes you may have like 99% accuracy on training set, but you don't celebrate until you see the result of testing set because it has seen the output of the training set before. But the testing set, the system has never gotten an idea about how it looks. So this is the one we are going to celebrate. After hiding the output of the testing set, and we now use our model to predict what's going to be the correct thing to identify, and we are getting excellent result, then we can then celebrate our testing set. So this is the idea that we refer to as generalization. And to do that, we already also clarified for us earlier. Usually there are two ways of dividing our data. We can divide it into two, the one we call hold out method. Hold out method. In this case, we are going to divide the data into two, 75% training, 25% testing, or 70%, 30%, 80%, 20%. It's okay. It depends if you are working on a particular task that someone already published before and you want to improve the result. It is good for you to use the same data partition that they have used. If they have used 80%, then use 80% also so that you can compare your work validly with them. However, if you have the first one to do it, then 80%, 20% is always good. 75, 25 is okay. However, people go for 90%, 10%, but we discourage it because the number of training sets is extremely huge compared to very small number of testing sets. Though it totals depend on the kind of data you are using. If you have very huge data, 10% may still be a very big data. Sometimes also you may divide the data into three. If you have more data, if the data is many, you have so much data, then you divide into training set, test, validation set, and then finally you have the testing set. It's all the same thing. Either 2 partition or 3 partition. If you can have even more partitions, 4, 5, you want to keep doing a lot of testing because you have huge data. There's no problem in that. After training and testing, you want to validate again before you deliver it to your client. You want to validate in the presence of your client. You ask them to give you more data from their farm. You can do that as many times as possible. What you want to avoid is you don't want to deliver a system to your client, and when they start using it, it's misbehaving. It's telling them the number of fertilizer to be used to get so yield, and it's not working because your model is bad. So that's why we encourage people to do as many validation and testing as possible. But sometimes the data is not available to do that. But at least the minimum is to divide into 2. And it's accessible every level. Another method is to use the resampling method. We call the n-fold, especially if your data set is very few. Imagine somebody having 16 sample, only 16 sample. So if you divide 16 sample to 70%, that is going to be too small. Then you may use what we call the n-fold crowd validation, which is this is the full data where you divide it to training and validation or training and testing set, only 2 division, which is fine. So then the data goes in here. You have the training set, you have the testing set with. Once you build the model, then you can take the testing set to come and do the work for you because we have only 2 partition, training and testing set. So sometimes when you have 3, training, validation, and testing set, in that case, you have the luxury of having this kind of diagram. See, you have your training set here, you have your validation set, all inside the building process. You can see this is for the building process. This one is outside. Testing set, this one is outside. Because this one will help you to do training, testing, do whatever you want to do here, and you build the model. Final evaluation, this may happen at the site of your client when you take it to your client, and it may also happen in your own developing site, but it's outside the development process to avoid data leakage. So, but sometimes when our data set is very few, we use what we call 10-fold cross validation. Here you are going to divide your data into 10 places. Let's say I'm having 1,000 samples. So each samples here, this is called fold 1. Fold 1. It will be like 100 samples. 100. Everyone will be 100. 100 times 10 will be 1,000. So when you want to do the training, you use all the n-1 partition to train. You can see here, from 2 to 10 partition, they are going to be portions. You are going to use for training. Then this one, you use it for testing. The next, this is you record the results. Maybe this one is getting you 91%. Then you go to the next one. This one will become part of the training, or the 9 portions. Then you use this one for testing. Then you record the result. Maybe the result here is 81%. You keep doing that until every portion is used for testing. Now it is the turn of the portion 10 to carry out to be used for testing. Once you have done that, then you are going to do average. You find the average of the result to be able to know the final result of your modeling. See, usually when you don't have an idea if something is going to work or not, we use cross validation to do the data partitioning. And sometimes also when you want to select hyperparameters, we recommend that people use cross validation. Divide your data into 70%, 30% keep it out of your modeling. Use that 70% for cross validation to check the hyperparameters. Because your testing set must not be used for parameter optimization or hyperparameter optimization. If you do that, that will lead to what we call data leakage. It means your testing set has been taken into consideration while optimizing the model, and that will not be valid. So once you have done that, this is just, again, revising for us how we break the data down. Now, the next is for you now. Let's do another demonstration. We're in practical demonstration, a case for predictive ML solution. Now, I've gotten another data set. We have demonstrated one data two times or so. I've gotten another data set that has more variables. So let's look at the data set together. Yeah. Yeah, this is called crop yield prediction, Indian states. This one has states, different states. So what we first of all need to do is to see, this is the data set. You can see a crop type, depending on kind of crop you want to plant. We have onion, potato, rice, and also further. The year of that planting, season. So which type of the season? Which state are they planting it? It can be a particular state, perhaps yield varies from state to state. The amount of fertilizer you need in the particular state will be different from the other. The area of the planting area. So you are looking at the targeted production, the production factor. We have annual rainfall. Then we have fertilizer. Then we have pesticide. These are the variables. Look at the variables, then you have the yield. The yield. Sometimes when you get data, you have to pay attention to the data. So when you say production and yield, if you feel a particular data is almost collinear to each other, that is, they are almost the same. What is production? What is yield? Are we getting yield from production? You have that particular luxury. You can remove some feature that you think may affect your model. Because in reality, how are you going to know the production that you are targeting ahead of time? So yield and production, they are things that we may have to decide later. So we may see that, okay, we may remove this as an input that you can do in Weka. But once you have your data in Excel, just save it as CSV. See, remember, Weka only accepts CSV file. You go here, you can say CSV, comma delimited. Then you select it and you save your file. So you are ready to go. So then the next thing is for you to go to Weka environment. See, Weka environment. So install your Weka here. I want to believe we can see my Weka environment. Can we see it? Can you somebody just type for me to be sure we are following? I'm sharing my full screen. Can we see the Weka being displayed? Okay, thank you very much. Thank you. Yeah. So you click the Explorer. So once you click the Explorer, that gives you, yeah. So you try to open your data. Open your data. It's inside this document, but it's looking for ARFF data. Some people contacted me before. They said, we cannot find our data when we open Weka. I said, because the Weka is looking for ARFF. That is the standard file for Weka. So you have to go here and say, look for CSV. Look for CSV data. Then my data will be pushed up here. You can see here, crop yield, Indian states. Open. You have the data loaded for you. And then you can visualize. You can look at each of the statistical characteristics of each variable. The minimum, the maximum, the mean, the standard deviations. You can visualize the distribution, the season of the year where they're planting, the state where it happens, the area, then the production, which I said may be collinear with. Then once you have that fertilizer, then you are ready to go. Any data that we don't like, any variable that we suspected that may affect our prediction, we can remove it. Like production and yield, we can check it. So we can try to see, okay, in the pre-processing, so we can try to see the correlation coefficient between each of these and the target. Which ones are correlated together. They will be able to see which one is likely going to affect what we want to build. So you can select all filter, unsupervised, looking for the attributes. And then we can try to see, okay, which of them can we use for system. We want to do attribute selection. See, we want to do attribute selection. So which attribute selection we want to use depend on exactly what we are trying to do. But for now, let us even try to run the experiment first. For the sake of people who are coming here for the first time, you go to classify. Choose a very simple classifier here. Let's say our lazy classifier, like K nearest neighbor. This is K nearest neighbor, IBK. IBK, K nearest neighbor. Show me your friend, I'll tell you the kind of person you are. One of the very simple algorithm in machine learning. You see, K is equal to 1 is the default. That if you tell me your friend, one of your closest friend, only one, based on that, whatever happened to that friend, I use it to tell us what may lucky to you. So this is the one I described today, the partition of the data. Here you can see the default is tenfold. Divide the data into 10 portions and use every n-1 for training and the last one for testing. And you keep changing it, the one I demonstrated earlier. You may also divide it into 2. Let's use 70% for training. And then once you say 70%, automatically 30% is reserved for testing. If you want to divide into 3, that is also fine. So you have to use training set. You supply training set. See, you're going to supply training set. Whatever you upload will be the training set. You upload only the training set. Data you can supply, testing set. Later you can supply another validation set. Later you can supply another validation. You can keep supplying and testing as many times as possible if you have the data. The more tests you carry out, the better, to ensure that the model you are going to release to your client is really worth it. So let's go for the percentage split. You have 70. So we say start. Now the model is building. You start to build a model that predict the yield. You can see now the result is out. The correlation coefficient is 92%. There's still room for improvement. The mean absolute error is there. Root mean squared error is there. Relative absolute error. There are so many quality measures that you check. You don't check only one. However, having 1 or 2 or 3 should be enough. For example, when I work with regression problem, I check for correlation coefficient and I also look for root mean square error and mean absolute error. But the way to do it is to look at the literature in that area you are modeling. What are the established performance measures that people use so that you can compare your work validly with their work. So this is provide the guide on the best one to use. So if you go and now you can try to, you can see we want to see the actual prediction. I told us earlier, we go here, more option. You tell it to tell us the output. I want to see the output. Presently it is null. Choose, tell me in plain text. I want to be seeing the result. Start. It will build it again, build the model again. Now this time around is going to display the predicted values side by side, the result. So by doing that, we are trying to see, okay, it's out. You can see here now it's showing me something here. You can see these are the testing set. Pay attention. The data is a little bit the big one. So these are the testing set, the 30%. The training set is not being shown because it's huge. And like I told you, even if the training set performance is good, we don't celebrate it. We only celebrate the testing set performance. You see, you can see here that it's giving us the result. Yeah. It's giving us the result. You can see here prediction on testing split. You can see it will indicate to you this prediction on testing split. It will also tell you how many time taken before it can build the model for prediction on the 30% test set. You can see this is the instance, this is the actual value, this is the predicted value, this is the error. You see, 1 point something. So you can see, you can make a plot. You can copy this data and then take it to Excel and make a plot to see how the predicted value is close or far away from the actual value. Look at this one now. The actual value is 0.79. The system is predicting 0.788. If you round it up, it's going to be 0.79. You can see. And regression is one of the very tough modeling to carry out. You can see here, so close to, very close to the number. So if your yield is supposed to be 0.79, maybe tons per acre, is predicting it as 0.88788, which is almost the same value. It means you can rely to some extent on whatever decision this system is given to you. And then later you can even move forward to investigate the feature selection. Okay, I want to see which of these features are contributing. See, bear in mind, we have not gotten the best result possible. If I want to get better result, I can increase my K to be 3. K is equal to 3. This is the hyperparameter value. Change the value of K, the value of neighbors you are using. And then run the system again and see what it's going to give you. Once you increase the value of K, it is expected that you may get better result. And you may not get. See, that is the principle of let the data speak. Now it has increased from 0.92 correlation to 0.98. Can you see? It means the result will be better than what we are even having before. Look at this one now, is 0.588. It is 0.575. The predictions are very close to each other. Just by increasing K to 3. You can try to increase it to 5, increase it to 7. You only stop increasing it when the value performance started going down again. Then you know that this is the best value I can use for this particular data. And it doesn't work across data. Your data, one data may be K is equal to 3, another data may not be K is equal to 3, and host of others. So this is a demonstration of this new data, and we are going to share this new data on the WhatsApp group so that people who want to practice it can then go and practice. And then this will also make us to be able to look out for our own data. See, data is expected, is said to be the next oil and gas. See, people who have access to data and they make effective use of it for insightful based decision making, they are going to rule the world. This is the way the life is going now presently. So that's why we can't afford to be left behind. It is high time we start documenting some of our data, because data speaks louder, but we don't understand their statement. And that is why AI is coming to help us understand what this data is saying. See, in the past, hurricane will just come and create a lot of disaster. But now, with data analytics being in place, 2 weeks before hurricane start or 1 week before, they will send a lot of alarms that there's likely going to be hurricane so day. It's not magic. That is science. It is data. Because hurricane does not just happen. 2 weeks before hurricane will happen, there will be earthquake under the sea. But we don't know, because we don't stay under the sea. There are a lot of things that take place under the sea. Even the atmospheric air will be different. Now with data analytics, we can gather those data and have an idea of what may happen, and we may prevent or avoid disaster where appropriate. So again, this is hopefully where we're going to be able to stay because of our time. So we welcome everybody on board, and we encourage us to explore, to practice some of the little that we've actually been learning. And then again, check it out as soon as the video is out, will be posted for us to check. We have a lot of guidance on our system. Let us try as much as possible to take advantage of it. See how you can implement it in your own area of specialization. Get any data, try it out. You learn data science, machine learning is an art. The more you practice, the more better you become. And everybody can actually take a lot of advantage, irrespective of the area of specialization that you actually belong to. So I believe with this one, we are going to say thank you very much for the day, and then we can take very few questions because of our time before we call it a day. Thank you very much.